This is Group 4's evaluation of the paper, 3D numerical simulation of aerodynamic characteristics of a gas filter. The purpose of the original paper was to investigate ways to improve the performance of gas filters used in engineering ventilation systems to protect against hazardous gases or aerosols, such as by using porous media and an explosion-proof plate. Some general reasons to create a similar paper would be to research ways to further improve the utilization rate of the filter paper. As a reminder, utilization rate is the measure of how much of the use time is actually used in productive work. Additionally, in the original paper, the authors indicated further optimization is required for other components of the filter, other than the porous media and the addition of the explosion-proof plate. In general, an expansion to the existing research on the topic would be useful since the original paper was published recently in 2019. Some newer reasons would be to investigate the effects on optimization of the number of pleats on the filter, flow directions, different geometries, such as the honeycomb filter geometry, and the distribution and thickness of the carbon layer. New ideas for a similar paper could be to investigate other types of porous media materials, specifically alternatives to activated carbon, and to compare the results obtained from simulations computed from one CFD software with a different CFD software with similar boundary conditions and geometry.
In reference to the original research paper, the current method for 3D numerical simulation of aerodynamic characteristics of a gas filter is governing equations for the flow through the gas filter while establishing boundary conditions. These equations were then solved using fluent and couple algorithms for CFD. A simplified gas filter was modeled with a single layer representing the filter itself. A few improvements or additions that can be implemented and were done in other papers include having a physical model and doing simulation over time, which led to discovering how time affects the flow. An improvement to the model could be having a complex, more realistic gas filter with multiple layers versus just having one layer represent the entire filter. A few papers mentioned using simple algorithms, so that could be in addition to the methods of solving the flow equations. Another improvement can be testing different filter types and materials versus just carbon.
To recall the main takeaways from the original paper, the authors used two methods to determine differences in the models: airflow and air age. They used CFD to highlight streamlines and identified large back vortices and limited flow-through area, both of which were mitigated with the explosion-proof plate. They also used CFD to identify air age within the filters. Low air age led to penetration of poisonous gas, whereas high air age led to dead zones. The explosion-proof plate improved the air age distribution in the filter layer, but not in the activated carbon layer. The thresholds for low and high air age were not explained well, but other papers used similar methods and governing equations, and based on those results, the conclusions of this paper were well-founded. As for their presentation of the research, the translation was poorly done at times, making it difficult to understand, and some diagrams, such as Figure 5, were not clear enough. The purpose of Figure 5 was to show that the air age in the carbon layer was largely unchanged, while the air age in the filter layer was drastically changed. This difference is difficult to see in the diagram, and could have been more clearly shown with separate diagrams for both layers. The authors set out to use CFD to research the effects of the explosion-proof plate in the function of a gas filter, and rightly determined that it played an important role in improving its performance. However, improvements could be made in the presentation and polish of the research.